All right. Hello, everyone. Thank you for joining today. My name is Heather Hoffman. I am the federal liaison between the WestFAST and the Western States Water Council and host of today's presentation. Please note this webinar will be recorded and posted to the WestFAST tab found on the Western States Water Council webpage at westernstateswater.org. So feel free to share that link with those who couldn't participate today. This webinar is part of a special webinar series on wildfire and water resources. And next month on May 18th, we'll hear from NASA's disaster program. So stay tuned for that, and please be on the lookout for announcements or visit our webpage for more information. Today's presenter is Tyson Ochsner. Dr. Ochsner works as a professor in the Department of Plant and Soil Sciences at Oklahoma State University and is from Chattanooga, Oklahoma. He earned a BS in environmental science at OSU in '98 and then studied soil science and water resources at Iowa State University, earning his MS in 2000 and a PhD in 2003. From 2003 to 2008, he worked as a soil scientist for USDA Agricultural Research Service in St. Paul, Minnesota. The mission of Dr. Ochsner's Soil Physics Research and Teaching Program is to help people better understand and appreciate the soil-water balance, and the surface energy balance, so that we can more wisely manage and conserve the land and water with which we have been entrusted. The primary focus is on a multi-scale soil moisture monitoring and improved utilization of soil moisture data in agriculture, meteorology, environmental modeling, and drought application. So with that fantastic introduction, I will pass it on to you, Tyson.
Okay, yeah, thank you so much, Heather. I'm going to try to share my screen here. See if we can do this. Okay, do you see my slides now?
I do.
Okay, great. Well, thank you, Heather, for arranging this opportunity. I really appreciate it, and thanks to those of you who have signed on here to listen today and to be a part of this discussion. I really am just honored that to have the chance to share this information. This is a seminar series that's been about the relationships between wildfire and water resources. And when we think about that, there's a lot of research and a lot of things that have been learned about what happens after the fire. How do those burns affect the hydrology and the water quality after the fire? This kind of turns it around, and we're looking here about how does the hydrologic conditions influence the fire danger and the probability of the fire occurring in the first place. And particularly, we're focused here on the role of the water that's stored in the soils and how we might better use information about the soil moisture conditions to better understand and predict wildfire danger. And so that's what I hope to share and visit with you about today. And just really looking forward to the discussion and your feedback as we go along. In the last few months, I have been working with a great interdisciplinary team to put together a review manuscript on this topic. And that manuscript is currently under review, but I just want to really thank and acknowledge the folks who have worked on that with me and have helped shape my thinking on this topic. And so it's folks from soil science, remote sensing, meteorology, forestry, and geography. And you can see their names here. Eric Kruger works with me here at OSU and has been really a leader in this research area for years now. Matthew Levi at the University of Georgia is another soil scientist working with us on this, along with his postdoc, Kevin Ching. John Bolton is with NASA Goddard and brings the remote sensing perspective. J.D. Carlson here at OSU, meteorologist and the leader of the OK Fire program. And then we have Nicholas Coop from University of British Columbia, who brings that forestry expertise. Zach Holden, who I think may be on the call with us today from U.S. Forest Service, and his modeling expertise has been a big part of that. And then Brian Magi at the University of North Carolina and Angela Rigdon. They both bring this remote sensing expertise as well. Angela has, I think, recently moved from Harvard University, and she will now be starting a position at UC Irvine. So our motivating question here in this work has been to understand how the increasingly available soil moisture information that we have can be used to better manage the impacts of fire on people, on communities, and ecosystems. And for me, this line of work really started a decade ago. It started back in 2012 with a project funded by the Joint Fire Science Program. And we went out and we started gathering data on rangelands here in Oklahoma. And so you can see Andres Patrignani, who was a student at that time. He's now an assistant professor at Kansas State, and he's installing soil moisture sensors in the rangeland. And for then subsequent years, we monitored the soil moisture conditions while also sampling the fuel loads and the fuel moisture to better understand these relationships. And so it has been, during that time, a sort of a decade-long journey of discovery for me as a soil scientist coming into this research area, really quite ignorant, to be honest with you, about what was going on. And so I'm just going to kind of run down a series of papers from this line of research. And so starting with Kruger et al. In 2015, we learned that if we look across the whole state of Oklahoma, there was a strong effect. Soil moisture had a strong effect on the growing season wildfire size here in our environment in the southern Great Plains. We followed that up with a modeling study that looked at the probability of a large fire occurring on any particular day in the state of Oklahoma. And we could see here that there was a different relationship in the growing season versus during the dormant season, but that in both cases, soil moisture conditions played an important role in predicting the probability of a large wildfire occurring on any given day. So that was published in Kruger et al. 2016. I think the slides will be available to you after the call, and the links should take you directly to these papers. That's why they're shown here as hyperlinks. As we were starting to present this work to people, we got some feedback, and people said, well, yeah, I mean, we know that soil moisture is important, but we just account for that by using drought indices. We account for it by using Keach-Byram Drought Index. That's KBDI, very widely used in the fire community. And so then we had to directly address that and do a comparison using measured soil moisture versus KBDI. And we could see that the measured soil moisture was a better predictor of the wildfire danger than this drought index that was being widely used. We then got into the mechanisms to really try to understand the mechanisms, and we're able to work with the data from this field experiment that you see here in the photo, and really able to start to draw out what are the relationships between the fuel moisture conditions, the curing of these fuels, how are those things linked to soil moisture. And those results are published in Sharma et al. 2020. And then going one step further, we looked at how does the actual load, the accumulation of the herbaceous fuels, how is that related to soil moisture? How can we use soil moisture information to better predict those fuel loads? And so I'm going to now just kind of talk you through this series of this sort of a journey of discovery here, going backwards, starting with the most recent here, Kruger et al. 2021, and kind of going backwards, and hopefully it will make sense as we do that. But we start off with the idea of we need to understand, if we're going to understand wildfire danger, we need to understand what is the fuel load that we have. And in our case, we have focused on these grassland systems which are the largest land cover in Oklahoma. And so we've developed a relatively simple modeling framework to predict these fuel loads. It starts with a sort of very widely accepted method for estimating evapotranspiration. So that's shown here as ETC. That's the sum of evaporation and transpiration. This is the FAO 56 dual crop coefficient method. If you're interested in those details, that may mean something to you, but it's a relatively simple equation shown here on the right side, where we have the evapotranspiration estimated as the product of the reference ET, that's the ET0, so the sort of the atmospheric conditions, multiplying a set of constants, or well, they're not really constants because they change day to day, but coefficients, I guess would be a better word here. So we can take weather data and estimate the reference ET using the FAO 56 method. And then we need some knowledge of the vegetation, particularly of its phenology, how it changes throughout the year. And we can estimate this basal crop coefficient or plant coefficient, KCB. And then we need to do a simulated water balance for the soil. We need to make some assumptions about drainage and runoff and try to simulate the soil water balance. And that lets us estimate these crop water stress coefficient, this KS, that accounts for how soil moisture deficits impact plant growth, and this evaporation coefficient, that's the loss of water from the soil surface directly. Once we have done that water balance and we have these coefficients, then we're able to peel off just the part related to transpiration. So the transpiration by the vegetation we can estimate by this reference ET times these two coefficients. And once we have an estimate of the transpiration, we can accumulate the transpiration throughout the season, normalize it, and multiply it by a water productivity, WP, which is a constant for a given species or maybe assemblage of species. And from there, we can get the biomass or the fuel load. So that's kind of the modeling approach. And we needed to calibrate the model at a site where we had measured the fuel loads and where we had measured evapotranspiration. And that's the site that I showed you in the prior photo. It's called the moist site. I can tell you more about that later if you're interested. But we calibrated the model. And so we have a system for predicting these fuel loads. But the thing we're interested in figuring out is how could we use soil moisture information? Because typically when we say, hey, we're using weather data, we're thinking of, well, I'm using all the things I measured above ground. That's good. Why not also use the things we measured below ground, right? Where do those fit in the model? Where do our measurements of soil moisture fit into the model? Well, we can just directly insert them. Instead of having to have a simulated water balance where we have to make some assumptions about drainage and runoff, we can just every day insert our observed soil moisture data to get these coefficients that we need for the model. And so we ran the model both ways, with a simulated water balance, and then again with just direct insertion of the soil moisture data. And we tested this across the state of Oklahoma using, as a surrogate for our fuel load data, we used hay yields that were estimated by the National Agricultural Statistics Service. So just a little bit of the nuts and bolts on this. You know, you have to calibrate and validate a model, and so we did that. And the green line here shows the measured evapotranspiration with an eddy covariance system. The black line here shows our model. It's doing pretty well, capturing the dynamics year to year of the evapotranspiration. Performed pretty well in the calibration period and again in the validation period. So after we've estimated the ET, we can peel out from the model an estimate of the transpiration. and try to go that next step to get the biomass. And so that's what this figure shows. On the x-axis here, we have the cumulative normalized transpiration. And on the y-axis here, we have the cumulative biomass. And the slope of that line is the water productivity for this system. And in this case, it came out to be 45 kilograms per hectare. That's what we got for this site. Okay, so we need some more testing. We need some more sites to sort of validate it and put some bounds on this number, because there's not a lot of values in the literature for native ecosystems. Most of the studies have been for crops. So anyway, that's what we have, and you can see using that value, we can actually get the seasonal accumulation of the fuel load. That's shown in the lower panel here. The growth rate essentially, and yeah, it looks reasonable. So it seems like it's doing a pretty good job of calculating the fuel loads, at least for this particular site. And then we apply that across the whole state. So just calibrated it at one site and then applied it across the whole state. Hey, it worked pretty good actually. So here's the modeled hay yield, which we get from our prediction. Again, in our context, this would be the herbaceous fuel load. And here's what was measured by the National Agricultural Statistics Service on the y-axis across 3 different years and 25 counties in the state of Oklahoma. And the model is sort of following along the one-to-one line here, as it should. And we have a Nash Sutcliffe efficiency of 0.65. Which is reasonable. This is by directly inserting the soil moisture data. If we try to make those same predictions with the same model, but we don't insert the soil moisture observations, then our Nash Sutcliffe efficiency is only 0.1. That's like an R squared value. So it's like an R squared of 0.1. That's not good. And the errors, the mean absolute errors, are twice as large if we don't insert the soil moisture observations. And so this is, I think, kind of a first step towards how we might make dynamic herbaceous fuel load models that we could use to better predict wildfire danger. Okay, so if we then are learning something about the fuel loads, the next thing in terms of fire we need to understand is the fuel moisture conditions. And we have learned that, at least for these grassland systems we've been studying, that the fuel moisture conditions are strongly linked to the soil moisture conditions. So this is a little bit busy kind of graph I want to show you. There's 2 years worth of data from our field sites. 2012 is in the left column and 2013 is in the right-hand column. On the x-axis, we have the months of the year from May through November. And on the y-axis, we have different indicators of moisture. So the top row here shows the soil moisture, and it's expressed here as the fraction of available water capacity, or FAW. So this FAW, or FAW value, is at 1 when the soil is effectively at field capacity, and it's at 0 when the soil is effectively at the permanent wilting point. So it's a normalized measure of the soil moisture conditions in the root zone. And so what I want you to see is that basically from early June in 2012 all the way through August, we had declining soil moisture conditions. This was a year of exceptional drought. The dashed line here going through all the figures in 2012 is August 3rd, which was a date when the soil moisture, the FAW, had dropped to 24%, and there was a large wildfire outbreak close to our study area that burned about 35,000 hectares and destroyed quite a few homes and structures in the region. So that's what the dashed line indicates. The next panel here is the green fuel moisture. This is what you would measure if you go out into the rangeland and you just find green vegetation, okay, and you sample the leaves that are totally green and you measure their moisture content. So you'll see this kind of dynamic. The lower panel is the dead fuel moisture. So this is what you would measure if you go out and you find, residue from last year's growth, or if you find tissues that have totally senesced from this year's production. So that would be the dead fuel moisture. It's much lower. But what I think is most important for the fire danger in these, at least these herbaceous fuel beds, is just the mix. What's the total fuel moisture of that mixed live and dead fuel bed? And that's the mixed fuel moisture shown here in the middle. So this mixed fuel moisture, you can see it declined right along with the declining soil moisture conditions, and it reached a minimum value right there in early August, just exactly when the fires occurred. And so that mixed fuel moisture, getting it down below some critical threshold, really raises the danger of these wildfires. In 2013, we had higher soil moisture levels and we had higher fuel moisture levels, except we did have a pretty rapid decline in fuel moisture in September of 2013, and that was coincident with a rapid decline in the soil moisture as well at that same time period. And that'll come back into the next slide I'm going to show you. So from this data set, that's the time series, but we really want to pull it out and isolate this relationship between the mixed fuel moisture and the soil moisture. And so that's shown here on this slide. So here we have now from that same data set, for periods when the system was drying down, for when the soil moisture was declining, we have the FAW, or the soil moisture rate, on the x-axis and the mixed fuel moisture on the y-axis. And you can see there's a region here where there's not much influence. There's a range of soil moisture conditions where soil moisture is not limiting and it's not influencing the fuel moisture. But once we drop below a certain threshold, which in this case was right around 60% of the fraction available water capacity, then we see this strong linear relationship. As the soil moisture declines, the fuel moisture is also declining. And we can go beyond that. We can let the system dry down even further. And if we start to look at the curing process, so curing is when fuels transition from live to dead. So we call that curing. And the curing process, as shown here in the lower panel, it really doesn't begin until the soil moisture conditions drop below a threshold of 30% in terms of the fraction of available water capacity. And so once we drop below this 0.3 level, you see the accelerating curing rate of these fuels. And the maximum curing rate that we observed was about 12.6 grams per meter squared per day. And that happened in September of 2013, which was actually the wetter year, but we had a late season drought there. Fall averaged 0.21, so very low soil moisture conditions during that time period. And just to kind of put this curing rate in perspective, research has shown that in grasslands like this, dead fuel loads of about 70 grams per square meter can support the spread of a wildfire. And so you can see, comparing the 12.6 and the 70, it would take 5 or 6 days of this kind of curing to create enough dead fuel load that could then propagate a wildfire. And so that helps put these curing rates in context. So now we've got perhaps a use of soil moisture for estimating fuel loads, a way we might use soil moisture for estimating the mixed fuel moisture in these herbaceous fuel loads, and then we can perhaps estimate the curing rate from the soil moisture conditions. All right, so now we kind of put together a synthesis figure that I want to share with you and walk you through a little bit. So this is now kind of a conceptual model, but it's based on data of exactly how declining soil moisture leads us to wildfire. So on the x-axis here, we have the soil moisture, again, as fall, ranging from 0 to 1. And on the y-axis here, we have the left y-axis, we have the number of large wildfires that occurred in the state of Oklahoma from 2000 through 2012. So a 13-year period. And these are large growing season wildfire events. The gray bars show the soil moisture conditions at which they occurred. The dark line here goes with the right-hand axis. It shows the probability of having a large wildfire in the state of Oklahoma given a certain soil moisture condition as shown here on the x-axis. This is for the growing season, and this line is for conditions where we have relatively high wind speeds and relatively low humidities. Okay. So just kind of walking from right to left in this figure. So grassland fuel moisture starts to decline right here at this threshold of around 60%. So that's when the fuel moisture starts to decline. The growth, the fuel production, we know starts to slow down when the fall drops below about 0.4. If the drying continues, then the curing process is going to begin. The onset of rapid curing is going to be at a fall of around 0.3, and then most of the large wildfires are at least in Oklahoma, are going to occur when the fall conditions drop below 0.2. All right, and so that's kind of a sort of a nice summary of what we have learned from our work here so far. Okay, so that brings us to today, the current situation. So now we have a growing body of research that provides pretty strong evidence, in my opinion, that soil moisture is a key predictor of wildfire danger, but it's not yet effectively integrated into our fire danger rating systems. And so I think if you're listening and following, you should be asking a question. Now, your skepticism should be firing up about right now. Okay, you should be saying, okay, Ochsner, listen, that you're just showing us data from Oklahoma. What about the rest of the country? What about the rest of the world? Okay, well, I'm glad you asked. I'm just going to highlight, I don't have time to go over this whole body of research. That's what our review paper is for. But I just want to highlight some discoveries from other groups and other parts of the world that are saying the same thing. This goes back, as far as I know, to about 2007. There's probably a little bit earlier stuff, but you can see this paper in 2007 where they showed that in situ soil moisture measurements were really strongly correlated with the live fuel moisture for shrubs in Italy in a Mediterranean environment. You can go to Siberia. So you can go to this study in 2009, which I think was maybe the first study to use remotely sensed soil moisture data. And they showed that high soil moisture conditions limit the extent of forest fires in Siberia. So that research came out in 2009. So now we have in situ, we have remotely sensed, and that also leaves then to modeling. We can model soil moisture conditions. And this paper in 2010, Slocum et al. Showed that low soil moisture conditions, as simulated by a model, were strongly associated with large wildfires in Florida. So now we've got a Mediterranean environment, we've got Siberia, we've got Florida, we've got Oklahoma. There's just from these kind of seminal papers, there's kind of a long list of research that shows this in other places around the world. I'll just hit two of the most recent ones. This paper from last year, Liu and Wei, showed that remotely sensed soil moisture can be used to estimate live fuel moisture to within an accuracy of about 20% across the entire U.S. They looked at about 1,000 sites across the U.S. This is a really nice paper. In this area, it's been surprising to me, but it's really cool. We're finding that soil moisture conditions influence dead fuel moisture and fire danger in forest. So this is a study from the foothills of the Sierra Nevada. And likewise, similar work in eucalyptus forests in Australia, forests in Thailand. We're starting to see this same kind of pattern emerge, that the soil moisture is having an important influence on the dead fuel moisture in these forest environments. And then finally, right back here to the western states, I really like this work by our colleagues Waring and Coops. This is Nicholas Coops. And they looked at available soil water as a tool for predicting where wildfires may occur in the western states and also western Canada. And so their red zones here are the places that they modeled to be at elevated fire danger due to limited soil moisture availability. And the black dots, if you can see those, are the places where the fires occurred. And so it's a lot of research from a lot of different places showing the value of soil moisture as a predictor of wildfire danger. Now, we still have a lot to learn. We've learned a lot, and we have a lot more to learn. So some of the key remaining questions, in my opinion, I think we still need to learn more about how to best represent the soil moisture conditions. Do we use absolute values? Do we use this fraction of available water? Or maybe we look at the soil moisture anomaly or a percentile. What's the best way to represent that? I think we still need to learn more there. What are the most relevant soil depths to consider? I think that's important, and that might vary from one ecosystem to another. I think we need to think about the different sources of soil moisture information. We have in situ networks, we have satellite remotely sensed soil moisture data, we have modeled soil moisture data. How do we leverage the strengths and weaknesses of these different sources? I think an area that really needs some more work is on the burning of organic soils. So, right, the soil itself can burn. Peat and humus and organic soils can catch fire and burn. And how is that influenced by the soil moisture conditions? I think we need to understand more about that. And then the relationship between soil moisture and prescribed fire, both, the intensity of the prescribed fires, the effectiveness of the prescribed fire, how is that related to the soil moisture conditions? I think we have more to learn there. And then probably most importantly is maybe this last one, and this is almost the end now, but how can wildfire professionals be convinced and enabled to use soil moisture information more effectively? And that's kind of the idea that I want to close with, because that's what I'm really motivated to understand. This diagram, it's a little bit busy, but it just represents a flow chart of the U.S. National Fire Danger Rating System. Very important system that we use here in the U.S. to understand our fire danger. This is the 2016 version of that system. And if you read all the fine print there, what you will not find anywhere is soil moisture. It's not used at all in any way. But I think it could be. I think we have the research maybe to look at ways to model herbaceous fuel loads using soil moisture information. I think we could look at maybe modeling the fuel moisture using soil moisture information. That would feed into these boxes. We could use perhaps soil moisture observations or modeled values to replace the Keach-Byram drought index. We already have the research to show that would be an improvement. We have opportunity to use soil moisture information to predict curing rates for herbaceous fuels. So these are just some of the opportunities that seem to be out there and seem to be supported by the research that we have thus far, although certainly there's more to learn. And so I just want to come back to that question. How do we get there? How do we go from the research to the actual application? And I think conversations like today, webinars like today, maybe can be a help and to help move us forward together as a community, cooperating, learning from each other, and helping each other until we get to that point where soil moisture information is routinely used to help us better understand and manage the impacts of fire on our communities and our ecosystems. And so that's what I wanted to say to you today. And I want to close just by giving some thanks to the groups that have helped support this work: the South Central Climate Adaptation Science Center, NIDIS, the National Integrated Drought Information System, the Joint Fire Science Program, and USDA. Big thanks to all my present and former group members who have helped with this, and the folks from the Oklahoma Mesonet, which are essential to this work. And I just invite you to get in touch. If you don't have a chance to visit with me now, reach out by email. You can get on our websites if you're interested in getting high resolution soil moisture data. We have that available online for the state of Oklahoma. If you work with vegetation, you might want to have this tool, this free app for measuring green canopy cover, which you can get here, thecanopeoapp.com. You can just learn about our soil physics program if you're really into that, or some of our research projects that are ongoing. The Rain-Fed Agriculture Innovation Network and the Rural Renewal Initiative are two of our big ongoing efforts now. So with that, I thank you very much for your attention and would welcome your feedback, your corrections, your questions.
Thank you so much, Tyson, for a very informative presentation. So yes, we will open it up for questions. You can unmute yourself and ask your question directly, raise your hand, or use the chat feature, and I can read your question out loud. Let's see, Roger has his hand up. Roger's up first.
Yeah, so thanks. Honestly, much of the first third of it went over my head. Something
Okay,
about an r squared plus 1. But anyway, it sounded bad. So on your last point, so is there a reluctance to use it, or you're just at the start of understanding that it's such a good predictor that now is the time to start taking it to those that hold or have the fire danger or fire risk? Sorry, I've got a dog kind of nesting over here. So is there a reluctance, or you're just starting and you need help to do that with using it as a fire predictor, or what?
Yeah, great question. Thanks, Roger. It looks like we could have a fun jam session there at your place. But yeah, great question. I don't know that there's a reluctance per se any more than just the sort of common, it's always hard for any of us to change our workflows and change what we normally do. And honestly, because at least in the U.S., there's been increasing severity and extent of wildfires in recent years. I feel like our fire management professionals are very often stretched to the max. I mean, these folks are asked to do a lot, and they probably are, need more support and more resources to be able to free up or give them the capacity to do new things, like start to include soil moisture information. And so I think, I don't know that it's a reluctance per se, it's just always difficult to start doing something new that we haven't done before. And I'd just love to see these folks get some more support in that effort.
And then a follow-up question, maybe not directed at you, but maybe to Mike Strobel. I think you're on. But with the soil moisture network, or maybe it's to Tyson first, are you guys plugged into the soil moisture network effort? And is that potentially a venue to help spread the news on, this is a predictive tool, right? Because I was thinking about, so what do we do about this? And it's more of a, raising red flags when we see that the soil moisture is getting to a point that this is where wildfires could.
Yeah. We yes, several of us on this effort are linked in with the National Coordinated Soil Moisture Monitoring Network, and I think it was maybe discussions in that group that helped Heather and I connect and sort of led to this webinar today. And it also led the review manuscript, which I mentioned, came out of a workshop that we had on this topic just about a year ago, last May. And that workshop was sort of coordinated and advertised through the National Coordinated Soil Moisture Monitoring Network. And that's also where NIDIS has come in and has played an important role. So yeah, there's a lot of different people coming at this from different angles and trying to work together on it.
Great questions, Roger. Do we have any other questions from the group? I have one for you, Tyson. So in previous webinars we've had in this series, we've talked a lot about communities and local community involvement and how important that is when it comes to managing wildfire resources and planning efforts. How do you see this could fit into community involvement and action from your work?
It's a great question. So I could maybe just speculate a little bit from our local place environment here in Oklahoma. And so in Oklahoma, the fire management community and our first responders, they really utilize and benefit from this OK Fire system, which J.D. Carlson leads. And that system includes not only delivering, data products like FAW, which is now part of their package of information that they give these folks, but it also includes training. It includes, workshops and one-on-ones and all kinds of training and support to help the folks on the ground learn how to use this information. And I think JD's actually on the line with us here. He might add more to that perspective as well, but that's how I see it.
Yeah, that's great. We'd love to hear more, JD, if you're willing.
Tyson, can you hear me? One thing I was thinking you could do, if we have time, is you could go to our website, OK Fire, and share that soil moisture map, which is directly based off of our research. And it's updated every 30 minutes based on the Mesonet's soil moisture network. And we say explicitly on the legend that it's good for only for the growing season, which we're soon in, May through October, basically. Or is it May through November? I think it's May through November. But anyway, even though that's not directly linked into the National Fire Danger Rating System from which we get our products, we offered it as another sort of standalone tool that people can use to look at the probability of having a large growing season wildfire in Oklahoma. And by large, we mean, and this is what in our research, anything over 1,000 acres was considered a large wildfire.
Yeah, great point, JD. I just put the link to today's map in the chat there, so if somebody wants to see how that information being packaged.
Fantastic. And I'll include all the links when I post the recording to our website, as well as the slides from today. So you'll be able to access them there after you leave the meeting. Other questions? Okay, we have one in the chat here from Todd. Does the National Weather Service incorporate soil moisture into their red flag warnings?
Not to my knowledge. Maybe somebody else on the call knows more than I do, but I don't
think
so.
No, it's based on, according to my understanding, it's based on the state of the fuels. If we're greened up or if we're dry, and then it's based. Then that knows what part of the state to concentrate in. And then the rest is just based on wind speeds, relative humidities, and things like that. At least in our state.
Good question.
Yeah. There aren't any others. I'll ask another one. So you mentioned several other studies across the world, really, right?
Yeah.
That you've accessed and are knowledgeable about. But do you have plans, or do you know if there are other plans to expand your study to other ecosystems, perhaps like sagebrush steppe or forests within the United States?
Good question. So certainly there are some studies looking at the links between soil moisture and wildfire in the forested ecosystems. And so the work of Nicholas Coops being one, and the paper that I mentioned from the Sierra Nevadas, and then other forested ecosystems around the world. The sagebrush one, I only think of one study off the top of my head, and that's from northern Utah. There was a study by Chi et al. The first author's name is QI. So Chi et al. 2012. They looked at fuel moisture conditions in sagebrush in Utah and saw that they were strongly linked to the fuel moisture and soil moisture were strongly linked in those sagebrush systems in northern Utah.
Okay,
So
great. Sounds like there is work being done.
I think so, yeah, and certainly lots of other places. I think the Great North, right? So the sort of Arctic environment is a place to look, and then the Everglades, the coastal regions in North Carolina and other. There's just a lot of different fire environments around the world, and lots of places where these relationships still need to be explored.
Yeah. All right. Well, we have a couple hands up. Let's see. Mike, you want to go first?
Thanks, Tyson. Thank you. It was a great talk. I appreciate it. When you mentioned the in situ networks and utilizing this information on soil moisture, obviously Oklahoma with the Mesonet system there is probably one of the best in the country. There's no question. Your concentration of information is really good. And with that, you have a valuable tool. Across the US though, and we're all part of this effort looking at the National Soil Moisture Network, that there are areas where the distribution of in situ networks are limited. In the West, I'd say probably close to 500 of the SNOTEL stations in the forested West have soil moisture. Other networks included in there give us some distribution, but what kind of a concentration would you estimate is needed? I mean, again, you're working with a great data set there in Oklahoma, but looking at it on a national level, what should we be focusing on if we wanted to use this as a fire predictor?
Yeah, it's a great question, Mike, which I can probably only partly answer. I think we have this distribution of one station like every 30 miles or so in Oklahoma, and that proved to be enough to really learn something valuable. More might be better. Less might be okay. We really don't know. We haven't done that research yet to really define that station density. But thinking nationally, I just want to point out that we need enough in situ stations at least to be able to calibrate and validate our model soil moisture values or our remotely sensed soil moisture values. And so it's really thinking about how do we leverage all of these things together. I'm an in situ guy. I would love to see 3,000 in situ stations across the U.S. all integrated together in a seamless network. I think we need to get there. We can get there. We're not there yet. But it makes me, I don't know, I hate to call out somebody, but if Zach Holden is still on and is available to comment just about the potential for modeling soil moisture conditions at the national scale and how that might link in with this fire danger situation. Zach, are you able to comment on any of that? He may not be available, so I'll just say that there are sort of high resolution modeling efforts underway that try to provide soil moisture information specifically for the purpose of fire danger rating. And so that's another promising avenue along with the remote sensing.
Great, thank you. All right, Marina has a hand up. Marina?
If I can get myself off mute.
We can hear you.
Yep.
Oh, shoot. Can you hear me now?
Yes.
Yeah.
And I'm going to try going on camera even. I apologize for the delays. Me and Teams don't have the best relationship. Well, anyway, if you can hear me, I'll just talk. So hi, Tyson. I want to kind of go back to what Heather was raising in terms of different ecosystems and specifically focus on, and this is more of a kind of a programmatic question than a scientific one, although it certainly relates to the scientific side. If we talk about wildfire, people sort of pretty immediately, well, at least in much of the country, or maybe the country I'm used to, go to the forests. Obviously from Oklahoma, you're focusing on the grasslands. I know you researchers are cognizant of differences that are going to obtain from those different ecosystems or fuel types. What's your reflection on how much we need to emphasize that from the get-go, or when do we start bringing in some, comment, discussion, clarification that we're talking about this kind of ecosystem versus that kind? Does it need to be front and center, or is there enough overlap that we carry forward kind of as a theme about wildfire, if I'm making any sense with this question? And if not, we can take it offline later.
It's a great question. It's partly a philosophical question. Somebody told me one time that biologists look for differences and physicists look for similarities. So I guess it depends whether you're fundamentally a biologist or a physicist. But it's always probably appropriate to be clear about where the data were collected and so forth. And so I showed obviously just a lot of data from Oklahoma. Now, the field sites where we worked were grasslands, and they were grassland fuels. But when we show data for the entire state, I mean, just recognize that 25 or more % of the state is forested. Many of those fires that I showed data for were in fact forest fires. And so it wasn't restricted to any one land use type. And as I've seen, looked at the literature from around the world, every new study I see that's just sort of showing the same patterns in a new ecosystem, it just kind of bumps up my confidence that there are certainly differences between ecosystems, but man, the soil moisture conditions are having an influence in every ecosystem that's been studied to date, to my knowledge.
Okay.
Thank you. All right, let's see. Roger has a hand up, and I know he and Forrest were having a chat in the chat boxes, but if you want to go ahead, Roger.
Yeah, so for our guests, I'm from EPA. I'm from the EPA Office of Water in DC, but I'm on the ground in Southern California and lead our Western water and drought work and a bunch of other stuff. And so I was asking our NASA representative about, because you had talked about remote sensing and the capabilities of doing that. So just was asking that question to Forrest in the chat. My follow-up question isn't really related to that, but it was one of the first questions I had is, so getting back to maybe the causes of the soil moisture issues, were you able to see, is that primarily a climatological issue? So is it just, it doesn't rain, or is it a maybe more anthropogenic? So what can we do about it when we see the soil moisture going in a certain direction? Is there something that we could do other than turning sprinklers on? But I mean, just trying to think if there's some way of mitigating so we stay more on the maybe the right side of that graph that you showed. Maybe not, but I was just asking the question.
A great question, Roger. I'm sure to a large measure I don't know, but I do know a few things. If you know, if we see that we're in a particular region is in a period of declining soil moisture levels and they're approaching some of these critical thresholds, then we can, start to enact policies, maybe burn bans or things like that, and we can start to sort of prepare or stage resources for wildfire response to those regions. And we have seen, at least from our studies here in Oklahoma, looking at soil moisture versus KBDI, we tended to get earlier warning, 1 or 2 weeks earlier warning of the wildfire danger if we use the measured soil moisture instead of relying on the traditional drought indices. And so it can help us with preparation. Prevention, I don't know. I think that's where one area I just briefly mentioned that I haven't seen much literature on. What about prescribed fire, right? In the long term, prescribed fire is an important part of wildfire prevention, right? And so how might we target our prescribed fire for times and places where the soil moisture conditions are such that we're going to achieve our desired outcomes of the prescribed fire? That might be another thing to do.
Did you have a slide on that, that 1 to 2 week?
No, there's a paper called Kruger et al. 2017, and it's linked from one of the slides. Sorry. And in that paper, it shows the earlier warning capacity of using soil moisture information.
Yeah, because if it, thinking about, if you brief decision makers, it's like, this is great. So what do we do? What do we do with this information?
Yeah.
And so if there's ways of really making that kind of correlation or connection about what to do with the information, other than working it into the fire risk chart thing. So
yeah, no, I really love your thought process there, Zach, because we do need to think about how do we get, or Roger, how do we get to action? I see it in the chat. Zach couldn't find his mute button earlier, but Zach, are you able now to say a little bit about the topo fire efforts and what's happening there?
I was trying to see if I could help with the muting, but
Yeah.
I don't think I can from my end.
I was going to see how can we unmute him?
Yeah.
But just to follow up on
Doesn't look
that,
like
that could be something, because you talked, NIDIS is an active participant and member of WestFAST as well. So, how they articulate wildfire risk on drought.gov or some of theirs might be a good toehold.
Yeah, good. Thanks, Roger. It looks like Zach's ready now.
I'm trying, you guys. I'm so sorry. My phone's giving me trouble. Can you hear me now on my computer?
Yeah.
Okay. Yeah, just real quick. I mean, Marina somehow found us and gave us some support to revamp TopoFire. So we're bringing that daily soil moisture product back online. So that will cover the nation. It's just a simple soil water balance model, though. So we really need to do some analysis to see how it performs, like in western conifer forests and regions of complex terrain. But it's running.
That's great. That could become a good resource for the community. And that's Zach, is that 250 meter resolution soil moisture? Is that right?
Yeah, that's correct.
Yeah, that's awesome.
And we'll retool we've already kind of retooled the Keach Byram drought index. That's, like you pointed out, in dire need of an update. So
right. Yeah. It was a pretty good technology in 1968.
Yeah, exactly.
That's great. It looks like Marina do you still have your hand up, or did you have another question? Might still be up from earlier.
I think it's up
Anyone?
earlier.
Okay. All right.
Sorry about that.
That's okay. Anyone else have questions for Tyson? We're at the top of the hour. Well, I think this was a really great discussion, and you may see some movement from this, Tyson, and you may get more attention than you need right now,
Well,
as far
yeah,
as
I
questions
don't
coming
need
your way. So,
I don't need any attention, but if we can help, I mean, because I've been happy to put some time and effort here, because it comes down to, really make stuff like this can really make a difference. I mean, you can
yeah,
save lives, you can protect ecosystems perhaps, and so it's worth an effort even for a soil scientist like me.
it is, and you present a pretty compelling case. So, thank you so much. Really appreciate your time and efforts, and thank you to everyone for joining. And like I said, we'll have all the information up on our website, and just want to wish everyone a great day.
Thanks, everybody.
Yeah, thank you very much. It was great.